Okay, now we're doing physical chemistry, just beginning chapter 4, section 1. We're going to be talking about material equilibrium. Remember, material equilibrium has two parts, reaction equilibrium and phase equilibrium. Now, reaction equilibrium means that chemical species 1 is in equilibrium with chemical species 2. For example, let's say we have some NO gas, which is brown, and it's in equilibrium with N2O4, which is the dimer version of the same thing, except it's colorless. It's a dimer. These two are, let's say those two are in equilibrium. Well, that'd be reaction equilibrium. Now, phase equilibrium would mean the same thing in two different phases. For example, let's say we have some silver chloride solid, and it's in equilibrium with, silver plus ions and Cl negative chloride ions in an aqueous solution. Like here's a test tube. We have some solid silver chloride on the bottom, and it's a saturated solution, or this is the saturated solution. So we have our silver plus ions floating there and our chloride ions there. These two are in equilibrium. That'd be phase equilibrium. Now in chapter 4, we're going to define two new state functions. One is capital G for the Gibbs free energy function, and that's going to be equal to H minus Ts. Remember, H is enthalpy, T is temperature, S is entropy. And then we've got capital A for the Helmholtz free energy function. And that's going to be equal to U minus Ts. Remember, capital U is the internal energy. And of course, T is still temperature, S is still entropy. We're also going to be learning eventually about the chemical potential mu, which is closely related to the Gibbs free energy function. Now remember, the natural variables of U were temperature and volume. So keep in mind then that the natural variables of the Helmholtz free energy function would be temperature and volume, and then the natural variables of the Gibbs free energy function will be temperature and pressure. Later on you'll see why that's important. Okay, continue on physical chemistry, chapter 4, we're section 2 now. What if we have a non-equilibrium system? Well, one, let's say we don't have phase equilibrium, but we do still have phase and thermal equilibrium. So here's an example of a system. We have some solid salt here, NaCl. We have some NaCl aqueous, but not saturated here. And we got some pressure holding it in. But this is a frictionless partition, so it can move around if we want. Okay, now the internal energy of the system initially, like the way it's drawn, is equal to the internal energy of the solution plus the internal energy of the salt, because internal energy is extensive. Likewise, entropy is extensive. So the total entropy is equal to the entropy of the solution plus the entropy of the solid salt. Now let's say we remove the partition. We're going to do this adiabatically, so Q is equal to 0. We're going to do this reversibly, and our work is going to be equal to 0. Therefore, our final entropy is going to be the entropy of the solution plus the entropy of the NaCl. And the final internal energy is going to be equal to the internal energy of the solution plus the NaCl. In other words, because Q is W and W is 0, then delta S is going to be equal to 0, and delta U is going to be equal to 0. Continuing chapter 4, section 2 of physical chemistry, now we're going to talk about what if we have a non-equilibrium system. Now the first example we're going to look at is what if we have phase and thermal equilibrium. Oh, wait a minute. Oh, what the heck? Okay, continuing physical chemistry, chapter 4, beginning section 2, we're going to talk about different non-equilibrium systems now. First thing we're going to look at is what if we have we don't have phase equilibrium, but we do have mechanical and thermal equilibrium. For example, let's say we have this solid NaCl, salt, and we have this aqueous solution of NaCl, but it's not saturated, and it's held together by the same pressure, and it has a frictionless partition inside of it. So with the partition there, exactly like you see it, the total internal energy of the system is going to be the internal energy of the solution plus the internal energy of the NaCl. because internal energy is extensive. Likewise, the total entropy of the system is going to be the entropy of the solution plus the entropy of the solid salt. Again, that's probably because entropy is extensive. Now, let's say we remove partition, and right away, look at it exactly the same way it is. We remove the partition adiabatically and reversibly. We're going to say that Q equals 0, work is equal to 0. Therefore, the entropy of the second state here is going to be equal to the entropy of the solution plus the entropy of the NaCl, just like before, because it's extensive. And likewise, the internal energy is going to be the internal energy of the solution plus the internal energy of the solid, because it's extensive, just like before. So what we're saying is, just for removing the partition, with everything else still the same, delta S is equal to 0, and delta U is equal to 0. But keep in mind, that doesn't imply that the change in entropy of mixing is going to be equal to 0. We would have to look at that separately. Now, if we wait for this to go towards equilibrium, we're going to have salt dissolving in the aqueous solution. So we will have less salt here and more salt in the solution, but at any time we could stop the process and analyze it, and what we said before would still be true, that the total is equal to the sum of the parts for both internal energy and for entropy. Continuing next, physical chemistry, chapter 4, section 2. We're looking at what happens if you don't have reaction equilibrium. If you're not in equilibrium. Now, second one we're looking at is no reaction equilibrium. For example, let's say we have hydrogen gas and oxygen gas. That'll officially go to water gas if you were to, light a match. But if there is no catalyst or spark to get it going, then you're going to be stuck with just the H2 and O2. You're not at equilibrium. So obviously, we're assuming we're at moderate temperature because if it was high enough, it would go spontaneously. And we're assuming just constant pressure. So we can still find the entropy and internal energy of mixing from both of those from the previous laws of thermodynamics we talked about already. Now, let's say that our system is not in thermal equilibrium. For example, let's say we have this bar, visualize it metal if it's easier, but it really doesn't matter. And one end is at temperature 1, one is at temperature 2, with those two different temperature, with those not the same temperature. One could be higher than the other, doesn't matter which one. So to analyze this, what you want to do is slice it into infinitesimal steps. For each one of those steps, just like before, you can find the entropy of this slice, the entropy of that slice, the entropy of this slice, and you add all those up to get the total internal energy or the total entropy. It would just be an integral instead of a discrete sum. So what we've learned here is that if you have any system, even if it's not in material or thermal equilibrium, you can still assign a value to it for both U and for S. Continue on physical chemistry, chapter 4, section 3. So what happens if we have a system that is not at material equilibrium? So here's our system. The dotted line here means we're not at material equilibrium. Something's going to go on in here. It's inside a container that is closed and impermeable to matter, but heat and work can go in or out. And then, of course, we have the surroundings around that. And it, of course, is just to keep things simple, is inside a rigid adiabatic impermeable container. Now we're going to go ahead and do an endothermic reaction. So we're going to let heat in, which means work might come out too. So we know the dQ surroundings has to be equal to dQ system. That's just conservation of energy. So the dQ plus of the surroundings plus the dQ of the system has to be equal to 0 at all times. Now we also know that the ds universe, it's equal to ds of the surroundings plus ds of the systems. And that is to be greater than 0 because we're talking about an irreversible process. It's irreversible because we're not at equilibrium. So remember, the ds of the surroundings is equal to dq surroundings divided by t, because we always assume that the surroundings are in equilibrium. But we also know that ds of the system is not equal to dq of the system over t, because, again, our system is not in equilibrium, so what our system is doing is not irreversible. Now, So ds of the system is greater than minus ds of the surroundings, which is equal to minus dq of the surroundings divided by t, which is equal to dq of the system divided by t. So we know that ds of the system is greater than dq of the system divided by t. But we do know then that the dq of the system is equal to dq irreversible. Continuing on physical chemistry, chapter 4, section 3. So we've got two equations here. One, the differential of entropy for the system is greater than the differential of the irreversible heat for that system divided by temperature. This is true for a closed system in thermal and mechanical equilibrium, but not at material equilibrium. At material equilibrium, then, we have that the differential of entropy for a system is equal to the differential of the reversible heat for that system divided by T. So combining those, we know that ds is greater than or equal to dq over T. Now, of course, it's going to be equal if we're at equilibrium, because that's a reversible condition. And then it's going to be greater than before we're at equilibrium, because that's when the system is still irreversible. Now, dq is therefore less than or equal to TdS, just multiplying by T, obviously. Now remember, the first law says that dq is equal to du minus dw, so substituting that back in, we know that dq is less than or equal to TdS, or is less than or equal to du minus dw. So we know now that du is less than or equal to TdS plus dw for a closed system in mechanical and thermal equilibrium, but going through a material change. Okay, finishing up section 3 of chapter 4 of physical chemistry. We're still talking about entropy and equilibrium, or the lack thereof. So let's say we have an isolated system and it is not in material equilibrium. Notice we have 3 arrows going up, just one going down to show that it's not in equilibrium. In an isolated system, the criterion for material equilibrium is the maximization of the system's entropy. Now, on the other hand, let's say we have a closed system, same scenario. It's not in material equilibrium, but it is in thermal and mechanical equilibrium. That's why we have 3 arrows up, just one down. It's not equilibrium. We can have work in or out, positive or negative W, and heat in or out. So Q can be positive or negative. In this case, the criterion for material equilibrium is the maximization of the total entropy. S total, remember, is equal to S of the system plus S of the surroundings. Continuing on physical chemistry, chapter 4, we're now beginning section 4. We're going to talk a little bit more about the Gibbs and Helmholtz functions. Let's say we have a process where the temperature and the volume are both constant. Therefore, by definition, the differential of temperature is equal to 0, and the differential of volume is equal to 0. So we know then that du is equal to TdS plus dW from before. And we're going to add SDT and subtract SDT. We can do that, that's just simple algebra, because that is equal to 0. Now remember, the differential of ST is equal to SDT plus TdS. So we're going to rewrite this one as du is less than or equal to dTs plus dW minus SDT. And we're going to move this one over here and combine them to get du minus TS is less than or equal to minus PdV for work, reversible PV work obviously, minus SDT. Now, we said dV is equal to 0, and we said dt is equal to 0, therefore these are equal to 0. So this whole thing, du minus Ts, is less than or equal to 0, because we're at constant temperature and volume. Now, we already mentioned this before, but to remind you, we're defining A as u minus Ts. That's called the Helmholtz function. So now we know that dA is less than or equal to 0, as long as you're at constant temperature and volume, and you're at thermal and mechanical equilibrium. And this is assuming PV work only. It's actually dA is equal to 0. That means you are at material equilibrium. Okay, continuing on physical chemistry, chapter 4, section 4. Now we're going to talk about the constant temperature and pressure process. Now, by definition, then we know that dt is equal to 0 and dp is equal to 0. Now we're going to do the same trick we did last time. We're going to start out with the first law and a couple substitutions. It says du is less than or equal to TdS minus PdV. But we're going to add SDT and subtract SDT, and we're going to add VdP and subtract VdP. And again, using the same trick we did last time with the differential of TS and the differential of PV. So we're going to du is less than or equal to dTS minus dPV plus VdP minus SDT. We're going to get all these over to one side, so we're going to get d of u plus PV minus TS is less than or equal to minus SDT plus VdP. And remember, we're at constant temperature and pressure, so these are both equal to 0. Also remember that H is defined as u plus PV, and G is defined as H minus TS. So we're going to say that the differential of H minus TS is less than or equal to 0, since we're at constant temperature and pressure, remember, or just that dG is less than or equal to 0. But again, this is only constant temperature and pressure. And remember, G is our Gibbs free energy that we defined. So here's two different diagrams. We're going to graph A against T for time, or G against T for time. But remember, A, we're only looking at constant volume and temperature. And this could be an endothermic or reaction or an exothermic reaction. It doesn't matter. But as we go to equilibrium, the differential of A is going to be 0, and A is going to get minimized. Likewise, at constant pressure and temperature, dG is at 0 is going to, and equilibrium is going to be equal to 0 because G is getting minimized. Continuing on physical chemistry, chapter 4, section 4. So now we know that G, A, U, S, and H are all extensive state functions. Now let's say we have a system connected to our surroundings, and we're going to allow heat to flow between them. We're going to do this at constant temperature and pressure, but we're going to do some sort of irreversible chemical or phase change in our system. And just to simplify things, we're going to say this is an exothermic reaction. So Q is going to be going out this direction, but it actually shouldn't matter. So, and we're going to keep it at thermal and mechanical equilibrium. So we can do, certain calculations. So the delta S of the universe we know is Q reversible over T. And this is true for any reversible isothermal process. We know that the delta S of the surroundings is going to be minus Q of the system divided by T, because Q system is equal to minus Q of the surroundings. So Q system, we're at constant pressure, then is going to be equal to QP, and we showed before how that's going to be equal to delta H. Now we know, since S is extensive, that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So that's going to be equal to delta S of the system plus minus delta H of the system divided by T. Now we're going to take all that and we're going to factor out a minus 1 over T. So we're going to get delta S of the universe is equal to minus 1 over T times minus T over delta S system plus delta H system divided by T. And that's going to simplify then to minus 1 over T times delta G. So delta S of the universe is going to be equal to minus delta G divided by T. Now this is kind of a nice trick because remember, delta G, it's of our system, yet we can find out a characteristic of the entire universe from it. But remember, this is only valid if we have a closed system, we're at constant temperature and pressure, and we're doing PV work only. Continuing on physical chemistry, chapter 4, section 4. So we're going to show you entropy versus our process, our reaction path. This is not time. We're not necessarily going from left to right on time or anything. It's just where we are in the process. So there is a certain point called the equilibrium. On either side, the entropy is less. So what that means is if we're on either point out here, that the differential of S is going to be greater than 0 for any spontaneous process. It's going to keep going that way until we get to the top, where ds is equal to 0. Likewise, for G, it's going to get minimized at equilibrium. So for equilibrium, the differential of G is going to be equal to 0. If we're not at equilibrium on either side, it's going to be going towards equilibrium, so the differential of G has to be less than 0. Now remember, H is pressure dependent. We have delta G is equal to delta H minus T delta S, but this is only valid at constant temperature, remember, because of this T term. So A is a function of the natural variables temperature and volume. G is a function of the natural variables T and P. U is a function of the natural variables T and V. And then H is a function of the natural variables T and P. We're going to explain why that's useful later in a little bit. So delta G could go down if either delta H is less than 0 or if delta S is greater than 0. We'll explain why that's important later on, of course. Okay, physical chemistry, chapter 4. We're finishing up section 4 now. Got a whole bunch of equations that we get just from algebra, basically, now. So delta H is equal to delta G plus T delta S. And of course, T is going to be the temperature of our system. Delta H is the total energy released from our process. Delta G is going to be the useful work. T delta S is waste. It's entropy, disorder. Now remember, G is defined as H minus TS, and H is U plus PV, so G is equal to U plus PV minus TS. And then of course, A is equal to U minus TS, and G is equal to A plus PV, just algebra. So dG is equal to dA plus dPV. Now that's going to be dA plus dPdV plus VdP. We'll just split that out from the definition of differential. Also dG, remember, U minus TS is less than or equal to minus PDV minus SDT. Or dA is less than or equal to minus SDT plus dW. Or dG is less than or equal to minus SDT plus dW plus PV plus VdP. Now let's just take that and assume that we're at some sort of process that's constant temperature and pressure. Then we'll end up with just dG is less than or equal to dW plus PdV, because dt is equal to 0 and dV is equal to 0. So then we get dW is equal to minus PdV plus dW non-work. So we're just saying there's two types of work here, pressure volume work and non-work, or non-pressure volume work. So dG is going to be less than or equal to minus dW of the non-PV work. Or just integrating that, we'll get delta G is less than or equal to the total work that's not PV. So what we can say is that any non-pressure volume work we get from a system has to be less than or equal to the minus delta G. Think about sign conventions, why we did that. And remember, delta G is fixed for any reaction. That's a property of the materials. So this here is going to be our maximum possible non-expansion work that we get from our process.